Hello everyone, welcome back to Technologies Discussion channel. For this video, I'd like to continue the discussion on digital communication. This video, I will explain what is actually Shannon-Hartley theory. Okay, so in fact, this Shannon-Hartley theory is very important to communication. So basically, this will be the objective of this video. Because of this theory, okay, so Shannon-Hartley theory, this actually give us three critical insight into communication system. So all this will be the objective of this video. Guys, this is my email. If you have any question regards on this discussion, please drop me an email. Okay, or if not, I actually prefer you guys to ask me your question through the comment. Before I continue, I'd like to urge you guys to help me by like this video. Just a few seconds. Help me. Press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Firstly, let me define what is Shannon-Hartley theory. Okay, so in fact, this theory is actually a fundamental result in information theory. Okay, so this equation here actually tell us that this is actually the maximum data rate which are able to send over a communication channel, okay, with noise but without error. So this will be the maximum possible data rate that I can actually bring it over from the transmitter to the receiver through the communication medium without any error, but definitely with some form of noise. Let's take a quick look on this equation here. This is the channel capacity. Typically, the SI unit is bit per second. This is bandwidth. Okay, so channel bandwidth. So this is defined as hertz. This is signal strength, and this is noise strength, and S over N actually stands for signal to noise ratio. I will explain a little bit more how to derive this equation on my next video. Let me use a very simple daily life analogy for us to understand Shannon-Hartley theory. Okay, so now imagine, okay, you are trying to communicate to a friend in a crowded room. So you will be the transmitter, your friend will be the receiver. Okay, so you are actually here, you are the transmitter, and your friend is actually the receiver. And basically, you are trying to shout over the air so that your friend can hear your voice. Okay, so basically, what are the simple analogies? The bandwidth is actually how wide your vocal range is. In fact, this actually describes how high and low frequency that you can actually pitch your voice. Next will be the signal S. This is the measure how loud you actually can shout over to your friend. Next will be the noise N, okay, which is the volume of the crowd that is actually talking around you. Imagine, okay, there are beside you and your friend, there are many people, okay, that basically separate between you and your friend. They are also discussing, so they actually create some form of noise. Next will be the channel capacity. Okay, so basically the channel capacity will be the maximum amount of information that your friend can understand in a second. So now with this equation, for example, if I want to increase my channel capacity, what can you do? You can actually increase, for example, your signal strength. You can shout louder, for example. This is what it means. You can shout louder. So when you actually shout louder, you actually increase your signal strength as here. Another way is you can find a quiet room. Okay, so when you actually find a quiet room, your noise actually reduce. So when you actually reduce the noise, the capacity actually will be increased. Or you can actually use a wider range of tone, okay, which means that I can actually has a wider range of tone, which means that the separation between high and low frequency is higher, and therefore with increased bandwidth, my channel capacity can also increase. So this is how you can increase your channel capacity. Firstly, okay, by increase the bandwidth. Second is to increase the signal strength, okay, which is how loud you can shout. Next will be reduce your noise. Okay, go to a quiet room, for example, here. Okay, so the theory, in fact, tells you the mathematical limit of how much information you can actually get across given this factor. So this is the maximum data rate. Okay, once you have the bandwidth, once you have the signal strength, once you have the noise, how much noise is in this room, this will actually give you the maximum possible data rate. So this is a simple analogy of Shannon-Hartley theory. Next, I'd like to explain why this theory is in fact a breakthrough. Okay, before Shannon actually has this equation, engineers in the past always believed that sending error-free message with noise is not possible. So this is the very old belief of the engineer. To send an error-free with noise is not possible. So somehow this equation actually proves something that is actually very surprising. Basically, this equation proves that error-free communication is possible even with noise, which means that noise, okay, even with some form of noise, error-free, okay, which means that we receive the message free of error is still possible as long as the rate must be below the channel capacity and the proper coding must be used. So this is the breakthrough from this equation, which means that although with noise, I still can transmit data from the transmitter to the receiver, and the receiver can actually receive the data error-free, even with some form of noise. So basically, as long as the data rate must be lower than the channel capacity, then this is possible. With this actually led to modern communication technology. For example, we have 5G, satellite communication, optical fiber, deep space communication. You can see that all these form of communication can happen in a long range and also a huge bandwidth. Next, I would like to explain why it is important for us to understand Shannon-Hartley theory. Okay, so in fact, for us as engineer, this theory actually set us a realistic target. For example, okay, if a communication system, in fact, they actually perform below the Shannon limit, which means that the data rate is actually lower than this Shannon limit, we know that there will be room for improvement. Why? Because this Shannon-Hartley theory actually gives us the maximum possible data rate. And let's say if this communication system perform below this limit, we know that there will be some form of room for improvement. However, on the other hand, if let's say that this is already at the limit, then we know that in order to improve the data rate or the channel capacity, we need to increase the bandwidth, or on the other hand, we probably can have a better signal to noise ratio so as to achieve higher speed. So basically, this is from the design aspect. For the real life aspect, okay, basically this actually explains why the internet actually slow down when you are actually further away. For example, the Wi-Fi router, okay, because the signal S actually drop. When the signal S actually drop, this actually lower the overall signal to noise ratio because the S actually drop, and therefore the signal to noise ratio overall also drop. And on the other hand, also probably this also explain why fiber optic cable is in fact faster than copper wire. This is because fiber optic cable actually has a larger bandwidth as compared to the bandwidth of the copper wire. With this, okay, before I just continue, okay, on my next session of discussion, I'd like to urge you guys to help me by like this video. Guys, just a few seconds, help me press the like button now. For those who are new to this channel, and if you have learned something from this video, urge you to help me by subscribing to this channel and turn on your notification bell. Once again, thank you so much for strong support. Let me explain the theory that in fact provide three critical insights into communication. The first one is basically this Shannon-Hartley theory actually give us the speed limit, which I have explained earlier on. Because this Shannon-Hartley theory, they in fact establish the maximum possible in terms of data transmission. No matter how advanced a technology become, it cannot reliable transmit data faster than the Shannon capacity C over a given channel without producing an unacceptable error rate. Okay, you can imagine this as a speed limit on a highway. So this is actually the first critical insight. The second critical insight is the trade-off. From this equation here, you can see the relationship between bandwidth and the signal power. In order to increase the data rate, okay, you can either increase the bandwidth or you increase the signal power. However, okay, basically, when you actually increase the power, okay, this may diminish the return, okay, because of this log function over here. So therefore, when you actually double the power, this does not actually double the capacity. It only increase it by just a very small constant amount. However, the best way to increase the channel capacity is to increase the bandwidth. This is almost direct proportional. So this is actually the second critical insight into communication. Next, coming to my third critical insight, okay, basically will be the obstacle. Okay, so basically it highlight that noise, in fact, is still the ultimate barrier in order for us to establish a error-free, a much huger in terms of the data rate, so-called channel. Okay, if there will be no noise, which means that n equals to 0, you can imagine if this is equal to 0, you can imagine that the channel capacity will be infinite, which means that we can send huge amount of data from the transmitter to the receiver through the communication medium. However, in the real world, noise is always present. So therefore, this capacity will be always finite, which means that there's no way that this can be infinite because the noise will be always present. So this will be the three critical insight into communication. Next, let me do a quick summarize what we have discussed. Okay, so basically from this theory, they actually say that we are not able to transmit data faster than the channel capacity without error, no matter what kind of encoding method that you actually try to use. So if you want a high data rate, you must increase your bandwidth, which is most significant as compared by increasing the signal power. So when you actually increase your signal power, you actually improve the overall signal to noise ratio. However, when you actually increase the power, this probably will give you so-called smaller return because of the log function here. So the example of the trend is when we actually double the bandwidth, this almost double the capacity. However, when we actually double the signal power, this probably will increase the channel capacity just slightly. So basically with this, I'd like to end my discussion. Please help me to like this video and subscribe to this channel. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.